Okay. Let's wait a little while when everybody drifts in, and we can get started. Hello.
Yes, we can hear you.
Good. Good. I can see that a few people are here. Dong Yap, I can see that you're here. Thank you for joining.
Yep.
Okay, let's just wait a little while before we get started.
Professor?
Yes?
Will only material from homeworks 1, 2, and 3 be covered on the exam, or will material from this week be covered as well?
I guess maybe the earlier part of this week, we might have some thing covered in the exam. But I would say that mainly from 1, 2, and 3 homework would be good. You would be safe. But if we have anything for this week, it will be earlier part of this week. I can look back at the past exam 1 and see what we covered, and give you a more precise answer. Right now, I would say that mainly the exam will be covering homework 1, 2, and 3.
Okay, thank you.
I can look at what I did last semester and give you a more precise answer. thing to do is exam 1. Okay, let's get started then, since it is about time, and that are there any questions before we get started? Well, if not, let's begin. I think one of the things that we found very interesting was the circular polarization of light. What it says is that if you have a light polarized in the x direction, for instance, this thing can rotate. So the electric field rotates. Okay, electric field actually rotates. Then it turns out that you can show that this electric field gives rise to angular momentum. Okay, and the reason why it gives rise to angular momentum is because you can show that this wave actually would have a wave that behaves like this, where phi is the angle of the vector making with the x-axis. And you can show that this wave can be written as a wave with increasing phase. In phi direction. Okay, it turns out that if you have a wave, like a plane wave, which we write as, let me see, I use like if I have a plane wave, like propagating in the z direction, and it turns out that this wave is increasing in phase in z direction, so it will have a linear momentum.
I have a question, Professor.
Yes, yes.
Do we consider right-hand polarized or left-hand polarized, or is just general case here?
This is true for both cases. The angular momentum will be of opposite sign. Okay, so the angular momentum comes about is because this can be written like a traveling wave in the phi direction. Just like when we have a wave traveling in the z direction, it gives rise to a linear momentum in z direction.
Yes, I mean here on your picture, the phi angle is directed, right?
Phi is, yeah, phi is increasing in this direction.
Okay, yeah,
Okay.
that's the
In
answer.
the direction of phi hat. Okay, so this wave can be shown to have increasing phase in the phi hat direction, and hence it can provide an angular momentum in the phi hat direction. And how we see this is this, that if you do have, say, for instance, a wave that is circularly polarized, and you can write the wave as E being equal to x plus or minus j y hat e to the minus j beta z. And then so we can actually write x hat plus or minus j y hat as being the same as rho hat plus or minus phi hat e to the minus or plus j phi. Okay, how you do this is to notice that x hat is a unit vector, and this x hat unit vector can be written in terms of rho hat cosine phi. minus phi hat sine phi. Okay, you can go to this picture again. You can see that x hat, which is this unit vector, will be rho hat cosine phi plus phi hat minus sine phi. You can go through the trigonometry component analysis over here. You find that x hat is due to rho hat and phi hat, and contributions are according to these components. Do you know how to work out this formula? Well, the way to work out this formula is quite easy. Say if you want to figure out in order to work out the coefficient alpha and beta, you dot this equation, say, with rho hat. Okay, if you do that, then you get rho hat dot x hat is equal to alpha. And then if you dot the same equation with phi hat, you will get that phi hat dot x hat is equal to beta. Can you see that? If you take the dot product of this equation, you can find alpha and beta very easily. And we know how to find the dot product between x hat and rho hat. Okay, the dot product between x hat and rho hat is just cosine phi. And then the dot product between phi hat and x hat is just minus sine phi. That's how we get this equation. And you can do the same thing for y hat. You go to the same algebra. Y hat is equal to rho hat sine phi plus phi hat cosine phi. Okay, now you plug this x hat and y hat into here. Okay, you combine the cosine and sine and cosine. You find that your x hat plus y hat can be written in this manner. Okay, you can combine cosine and sine into this exponential. You can combine the other cosine and sine into that exponential with a different sign. But what does this indicate? This essentially indicates that this is a traveling wave. E to the minus j phi is a traveling wave in phi direction. Okay, because it's a traveling wave in the phi direction, it has angular momentum. Another way to look at it is that you can think of this wave like e to the j phi as e to the minus j k phi phi. Okay, so this expression makes it look like a traveling wave. But what you're actually doing is that you're defining k phi to be 1 over rho, and then your phi is rho phi. Okay, from I shouldn't say this. So this should be a rho here. Okay, this is like arc length. Okay, so rho phi is arc length. Is the arc length in this? Let me write arc length properly. So this is like a wave number times a distance, and distance is arc length. The wave number is 1 over rho. So you can think of this as a traveling wave, but the wave number actually becomes smaller and smaller as rho becomes larger and larger. So if you think of this as a traveling wave, if you think of this as a traveling wave in the phi direction, the spacing between the peaks of this traveling wave becomes bigger and bigger, which means that the lambda in the phi direction becomes bigger and bigger as you go further and further away from the origin. And this is a characteristic of this traveling wave. And it has angular momentum, okay? So this fact has been exploited by some people in the optics community, that you will have a circularly polarized light. You can actually pass it through the radial analyzer. This radial analyzer would make this into a, say, I guess, radially polarized light. Okay, radially polarized light. And then it passed through this, what we call the spherical phase element, spectral phase element. And then this spectral phase element will convert the phase or remove the phase. Let me see what the proper name for this is. It's called a spiral phase element. Okay, let me write the proper name for this. This is called a spiral phase element. And what it does is that it is made of a dielectric slab of different thickness, depending on where you are on the angle. Because it has different thickness, it has a phase compensation property that it will remove this phase dependence. Okay, we'll remove this phase dependence. And then because if you have removed this dependence of the phase, then the light becomes either polarized in the rho direction or polarized in the phi direction. And then you can pass through the halfway plate. You will learn the halfway plate is something that will rotate the polarization of the wave. And then you get a cylindrically polarized where the electric field is pointing radially. And this kind of light wave has special property that they can be focused very, very radially. And optics people are very interested in this. And I thought I'd bring this up because it has something to do with circular polarization. Okay, let me put autosave on so that I don't have to worry about saving this. And there's another thing that I'd like you to learn about linear momentum is that in general, if you do have a wave that is linearly polarized and traveling in the z direction, you can show that the wave actually would have a linear momentum. Okay, let me get rid of these things. And the idea is that we know that if you have a plane wave, the power flow okay, is E cross H. It's the power flow. It turns out that the momentum of a plane wave is also very much related to this expression. The momentum G, okay, is usually defined as mu naught epsilon naught E cross H. Okay, and sometimes this is written as D cross B. Okay, this thing is called the momentum density. Of Maxwell's equations. And the derivation is rather complicated, but let me give you a very simple-minded derivation of this momentum density from a particle viewpoint. Okay, if you use the particle nature of light viewpoint, you can actually derive this quite easily because it has been discovered that light actually is corpuscular, which means that light is actually consists of photons. Each photon carries a packet of energy, which is h bar omega, okay? And then it also has been discovered later that the momentum of each photon has a number given by h bar k. And this is actually h bar omega over c. So if you take the viewpoint that the energy will be h bar omega times n times C. Okay, if you take the energy of each photon, multiply by the photon density, you think of a section where all these particles zipping past, like water flow, okay? And there were n photons per unit volume. Then the number of energy that you have per unit volume is proportional to the packet of energy that each photon carries times the number of photons you have per unit volume. But since this energy is traveling at the velocity of light c, this is power flow. This is E cross H. Okay, this is power flow. Okay, so from this very simple formula, you can see that using the fact that this is also H bar omega over C n times C squared, and this is just H bar K times n times C squared, and this would be momentum per particle. And momentum per particle times n gives you the momentum density. So this is momentum density. So you have the general relationship that E cross H is the momentum density times C squared, okay? Which is essentially this relationship over here. E cross H is G times C squared. So it's a very simple derivation for a plane wave using the particle picture. More complicated derivations are given in Kong and Jackson. Okay, you have to go through a lot more linear algebra and tensor algebra to arrive at this very simple relationship. But this is a very simple relationship for momentum density. Are there any questions for this? So it turns out that if you go into the particle picture of light, this derivation can be made very, very simple, okay? If no question, let's move on to complex Poynting theorem. We have studied instantaneous Poynting theorem before. We even studied complex Poynting theorem later on. We like to use complex Poynting theorem to arrive at what we call the lossless condition. Okay. And we learned this before, which is that if you take instantaneous Poynting power, this is instantaneous power density. If you time average it, okay, which I denote by this square bracket over here, which is time averaging. Time averaging means that you perform this integration over a large time and then over and divided by time to average it. This is essentially an averaging operation. Okay. And what do you think we learned this to be? I think we went through a lengthy proof in one of the lectures that if you were to do this, it can be expressed in terms of the complex Poynting power, Poynting vector. Does anybody remember what the right-hand side should be? Does anybody remember this? Maybe I can also ask you in circuit theory, that is, if you have a time harmonic signal, I'm assuming that this is time harmonic. Okay, you learn from circuit theory that if a signal is time harmonic, you multiply the voltage with the current, you get the instantaneous power. If you time average this,
Is it
what
zero?
do you get? What is that again? Somebody say
Zero?
something. Not zero, then the course will not be very interesting if it's zero. So it must be equal to something more interesting than zero. And it cannot be zero. Let's assume that this goes as cosine of omega t. And the current is also sinusoidal, cosine of omega t plus phi. If you multiply this out, you will have two terms. The second term is cosine omega t cosine phi minus sine of omega t sine of phi, right? You multiply this thing, you will have a term that is proportional to cosine square omega t cosine phi. And then you have another term that's proportional to cosine of omega t sine of omega t sine of phi. You will take the average of this. Would the average of the time, would the time average of the first term be zero? Can you see that?
No, will be
No, it's not zero, okay? If you take a cosine square function, cosine function looks like that. If you take a cosine square function, it looks like that. And if you time average this, it's just half, okay? So this time averages to half. The second one can be written as 2 cosine, 2 sine of 2 omega t, okay? Can be written as such if you use the trigonometric identity. The second term does average to zero, okay? So this thing doesn't time average to zero. And if both of these are time harmonic, this term wouldn't average to zero too. Do you remember what it averages to? It's a very important formula that you should memorize, both in circuit theory as well as in electromagnetic theory. Can everybody say what that average should be? We have to commit this knowledge to memory because it is a very important piece of knowledge. Anybody?
Is a half of a pointing
Yes.
vector.
Yes? Somebody say something, but I can't hear it.
Half of a pointing vector.
You have the half, the real part of the complex pointing vector. Okay. Let me put on my earphone, maybe I can hear better with my earphone on. Okay, it should be half the real part of E R omega cross H conjugate R omega. Okay, so this, do you remember this? This would be a complex conjugate. And so what should this be equal to? By the same token, is half the real part of B omega I conjugate omega. Well, these are phasors. Okay, these are phasors. These are the phasors or phasor representation of the time harmonic field. This is a very important formula. It can be proved very easily. So I encourage you to commit this to memory so that you would not forget this, okay? Please commit this to memory. So then, because of the fact that E cross H conjugate has a physical meaning of time average power or time average Poynting vector, we will take the divergence of it. Because divergence is always something to do with conservation, because divergence of J is equal to minus d rho dt, for instance. This equation has the meaning of charge conservation. Okay, so let's take the divergence of this to mimic this charge continuity equation to see what we can get out of here. And of course, if you use the vector identity for the differentiation by parts, you first keep h a constant and just differentiate this. If you have that, then this becomes h dot curl of E. And then the second thing you should do, as is often done in differentiation by parts, you keep E a constant, okay, and then just differentiate H. Okay, this is called the product rule. If you differentiate the product of two functions, you get this as a result. Is everybody familiar with this rule? Well, now we can make this simpler by using the fact that curl of E is minus j omega b. This essentially is just Faraday's law. And then curl of H is equal to j omega d plus j. Okay, but since we have conjugation of the H field, we'll take the conjugation of this equation and give us this equation. Now we can use these two equations to simplify what you have on the right-hand side. Okay, we can simplify the right-hand side of this equation using two of these Maxwell's equations. And we also put in the constitutive relationship for anisotropic media. So that B is mu dot H. And then D is epsilon dot E. But since we have deconjugation here, okay, we must well conjugate this equation as well. Okay. And then what we have then is that a curl of a divergence of E cross H would be equal to minus j omega H star. And then I'm going to replace curl of E with this equation over here. So by so doing, I get j omega dot b. That's how the j omega come about. Okay. So this term just becomes that term. And then now I put in curl of H with this substitution. Then what I have is that I would have plus j omega E dot D conjugation minus E dot J conjugation. Can you see that? I substitute in curl of H star with this expression. Then this term just becomes two terms. The first term is E dot with this term, which gives me this term. And then the second term is E dot with curl of H, which is this term, which gives me this term. Can everybody see the right-hand side? Okay, can everybody see that? Yes or no? Yes, no?
Yeah, we can see.
Yes.
Okay, wonderful. Yes, then I can move on, okay? Then I am going to use this constitutive relationship further and write this as j omega H dot mu dot H. And then the second term, I'm going to use this constitutive relationship and write as j omega E dot epsilon conjugation dot E star, and then put in the E dot J term at the end. Okay, I suppose this is easy to see. You just replace B and D with these two equations over here. And what else should I do next? I have divergence of E cross H is equal to this. I want to derive a conservative law, okay? And the thing I should do then in the conservative law is actually to integrate this, okay? Integrate this over a certain volume. Okay, I can integrate this over a certain volume. And then I would say that if I integrate this over a certain volume, say the volume V is here, bounded by a surface S. I'm going to integrate over this volume. What would the left-hand side become if I were to integrate this over a certain volume? What can I use to simplify the left-hand side? Anybody?
Gauss divergence theorem to count.
Yeah, I can use Gauss divergence theorem and convert the left-hand side into something that looks like a surface integral. Okay, and the surface integral will look something like this. Very good, very good. At least you're following. Okay, and then the right-hand side would be equal to the integration of the two terms. Okay, right-hand side, this is left-hand side, equal to that. Will be j omega, then integration of the two terms that I have, which is dv h dot mu dot h, which comes from the first term, and then the second term is, because I pull out a j minus omega outside, the second term just becomes e dot epsilon star dot e conjugate, okay? And then I will have left over the last term, integrated over volume. And this is integrated over volume, e dot j star. Okay, right-hand side just becomes this. Okay, are there any questions so far on the derivation? I guess you follow this, right? So you have learned about complex Poisson theorem, but what I want to show you here is actually when would a medium become lossless? Okay, when would a medium become lossless? Okay, so a medium would be lossless if, say, if this is a lossless medium, and what it means is that whatever power flowing in must be the same as power flowing out. Okay, so if this medium is lossless, whatever power that flows in must be the same as the power that flows out. And how we can express this is the divergence of E cross H is equal to 0. And if this is true, this would mean that, let me see, I should put a close circle over there, okay? What this means is that if I were to use Gauss divergence theorem, this would become ds E cross H star. And this would be 0, okay? If the medium is lossless, if I were to integrate E cross H over the entire surface, okay, whatever goes in has to come out. And this integration will become 0, okay? And I'm going to make j equal to 0 inside. So there's no j in there. So I can throw out the last term. So if j is equal to 0, I can throw out the last term. So if I integrate the left-hand side, okay, it becomes this. It has to become 0. Left-hand side becomes 0 as I perform this surface integral, okay? So what it says is that left-hand side is equal to 0, and then must be equal to the right-hand side. The right-hand side is just that integral that we had, minus j omega dv h dot mu dot h with a star here, minus e dot epsilon star dot e star. Okay, assuming no source inside the volume V. The volume V is lossless. And when would this be 0? Okay, when would this be 0? This would be 0 actually, I have to say something more. I have to say something more before I claim that this is zero. Let me see. What is the thing that I have to say? Okay. If something is lossless, it's the real part of this should be zero. Okay. It is the real part of this that has to be zero. Or you can put the real part in there too. What it means is that the Poynting vector need not necessarily time integrate to zero, but the time average power flow should integrate to zero because power is conserved. Whatever goes in must come out. So this should be time average power flow. So I will have the left-hand side equal to zero if I have to take the real part of the whole equation, okay? So left-hand side is equal to zero. That means that if I take the real part of this equation, okay, then it will be the real part of this equation. And this would be the real part of this expression over here. And this is time average power flow, and it should integrate out to be zero over a closed surface. So if the medium is lossless, this should integrate out to be zero. So our question is that when would this be zero? Well, I can rewrite this to be, let me see. This would be zero if whatever we have in here is completely real. If this quantity is real. If that quantity is real, what it means is that it becomes a purely imaginary number. It becomes a pure imaginary number. And then if you take the real part, you will get zero. Okay. So when would H star dot mu dot H become real? Okay, when would this become real? Well, there is a matrix theory that says that if you take a vector conjugate transpose dot with the matrix and dot with the vector itself, and this would become purely real if A has some certain special properties. So this knowledge follows from matrix algebra. Does anybody know what that statement is? What kind of property must A have if this quantity is always going to be a real quantity?
I guess it should be Hermitian.
Yeah, A is Hermitian. So if you show that A is Hermitian, very good, Ivan. If A is Hermitian, okay, no matter what letter A you put into this equation, it always gives you a real value. Okay, what does it mean when A is Hermitian? A is Hermitian means A Hermitian conjugate is A. And this symbol here means A conjugation transpose. This dagger here means conjugate transpose. Okay, so if mu is Hermitian, then they will always ensure that this quantity is real. Okay, and also by the same token, if epsilon star is Hermitian, okay, then you can always ensure that this quantity is always real. And if that is the case, then whatever you have inside this thing is always real. Okay, if this thing is always real, then the whole thing would be pure imaginary. And if you take its real part, it's always equal to zero. So the chain of thinking is that you take complex pointings theorem, which is what we have written down previously, okay? And then you integrate the left-hand side and the right-hand side. And if you take the real part of this and integrate, that thing should integrate out to 0 because of energy conservation. And it integrates to 0 if the medium is truly lossless, okay? And in order for that to integrate out to 0, it has to show that this part must be pure imaginary, implying that this part inside here must be pure real. If this part inside here is pure real, it's pure real for arbitrary H field. E and H can be arbitrary, okay? Otherwise, you can always say that what happens if these two terms cancel each other? Then it gives you 0. You can still have a real quantity without mu being Hermitian. But we're taking the case where H and E are arbitrary. So the only way for this thing to be always real is for mu and epsilon to be Hermitian. And this will ensure that this is pure imaginary. And then when you take the real part of it, then you always have a lossless medium. So the take-home message is that, well, if mu is mu conjugate epsilon is epsilon Hermitian conjugate, then we have a lossless medium. Okay, so let's do a simple sanity check. Say if epsilon is a plasma medium, we already showed that if we have a plasma medium, epsilon is given by this. So this is a very special case. This is not even an isotropic. This is isotropic. Okay, isotropic medium is a special case of an isotropic medium. So if I ask you to do this Hermitian test on this epsilon, is this thing Hermitian? Is this Hermitian? Well, you can, maybe it's hard to think because I suddenly switch over from using a tensor notation to a you can think of a tensor for an isotropic medium is just a scalar times identity matrix times a scalar, okay? So if this is going to be a Hermitian tensor, what does epsilon have to be? If it's always going to be like this in the relationship, or isotropic medium is just a scalar times identity tensor. So what would epsilon be in order to make epsilon a Hermitian tensor? Anybody? Is I a Hermitian tensor? Is I Hermitian? Anybody? Well, let's ask the question of what does Hermitian mean? Hermitian tensor means that if you take this I and then do a conjugate transpose, it is itself. Okay, but what is the identity matrix or tensor look like? It's 1, 1, 1, 0, 0, right? If I write it in full, it looks something like this. So 1, 1, 1, 0, 1, 0, 0, 0, 1. That is the identity tensor. Is this Hermitian?
Yes.
Yes, very good. So in order to make the entire thing Hermitian, what does epsilon have to be? In order for this to withstand the test that this is equal to that, epsilon has to be a real number, right? Can you see that epsilon is real for Hermiticity? Okay, that is the big word for being Hermitian. So a plasma medium is definitely a real number, and hence it is a lossless medium. Okay, can everybody get that? What about if I have a conductive medium? I would have epsilon naught minus j sigma over omega. And this is a complex number. Is this tensor that corresponds to this conductive medium Hermitian or not? Is this Hermitian?
I guess it's no longer Hermitian.
That's right, it's no longer Hermitian because if you plug it back here, this is a complex number. If you take its complex conjugate, it's not itself anymore, okay? So a conductive medium is not satisfying this property, and hence a conductive medium is lossy, okay? So these are just some of the sanity check. And you have to go back and think about it. Maybe it's too hard to think when I throw symbols back and forth between tensors and scalars, okay? So go back and meditate on this point and try to understand this point. And using this point, you can easily figure out what should be lossy and what shouldn't be lossy, okay? Any questions so far before we move on to a different topic? Okay, this is a very useful piece of knowledge. I think it should be something that you should keep in mind. But next I'd like to talk about energy density in dispersive medium. Okay. This is an interesting topic because we know that energy density for non-dispersive medium is given by energy density for electric field is half epsilon naught E squared, for instance. Okay, energy density for magnetic field is half mu naught H squared. Okay, this is non-dispersive medium. Do these two equations make sense to you? It probably is something that you have studied before in your undergraduate days too. You recognize that if you have electric field, it stores energy. The energy density is given by the first equation. And then if you have magnetic field, it also stores energy, and the energy density is given by the second expression. Okay, does this make sense to you? Okay, so it makes sense to you, but these two formulas do not hold true for dispersive medium. Not valid for dispersive medium. And we want to derive what the energy density should be if the medium is dispersive. So the derivation is kind of long, but it's written out very carefully in the lecture note, okay? What we do here is to assume that the field is almost time harmonic, is given by a complex number times e to the j omega t. So if you take the real part of this, you will get almost a time harmonic field. And then the H field is given by this quantity, which is complex. And we will make sure that omega is not purely real. Omega is something with the real part times subtracted with a small imaginary part. So omega is a complex number. So this is no more time harmonic, not time harmonic anymore. Okay, it's not time harmonic anymore. But when omega becomes real, these are really just the time harmonic fields. You take the real part of this complex field, or you take its imaginary part of this complex field, you will get time harmonic signals. But in order to be able to derive this energy density for dispersive medium, we use this approach of working with complex fields, okay? And if you do that, then what you have is that you can take the divergence of this quantity now, divergence of E cross H. And since these are solutions of Maxwell's equations, you can very easily show that even though you write the field in terms of complex numbers, they are still solutions to Maxwell's equations. And then again, using the identity that we had always done, these are complex fields. I'd like to put a complex conjugation on the second term, okay, because these are complex fields now. And then using the vector identity that we always had, let me just remove the space dependence and just emphasize on the time dependence. Okay, that doesn't mean that space dependence is no more there, but it's still there, but I just want to de-emphasize it. Okay, using the product rule for differentiation, I will end up with this expansion. And this product can be found in the, like the formulas I hand out in the supplementary material for the course, okay? And then now you use Maxwell's equations to substitute in for curl of E, you will get just J omega mu H, okay? And then I use Maxwell's equation to substitute in for curl of H star. Okay, I would just get J omega star epsilon star ET star, okay? So this equation should be derivable from Ampere's law, which is J omega epsilon E, okay, which is just given by that. But since I take complex conjugation, I have to complex conjugate the whole equation. I will get this J omega star. Omega is not the real number anymore in this derivation. I will have a minus sign coming out from this J that cancels this thing. I will have this expression being looking like this, okay? So things are going to get a little bit more complicated because omega is not the real number. Okay, omega is not the real number. And I'm going to make things a little bit simpler by assuming that omega is not the real number. But this field, E cross H conjugate, is not a constant anymore independent of time because this E is proportional to the E to the J omega T. H star is going to be proportional to the E to the minus J omega star T. Okay, if I take the conjugation of E and H, because E and H would both be dependent on this, but if I take its complex conjugation, I get this. And what it means is that E cross H conjugate star would be proportional to E to the J omega T, E to the minus J omega star T. Okay, it will have this very strange kind of time dependence that you never had before. Because omega is a complex number, then it's E to the J omega minus omega star T. And then if you work this out carefully, omega minus omega star is just the imaginary part. So it's 2 omega double prime T. Okay, So in other words, this power, this all E cross H conjugate grows with respect to time. Actually, it's not a constant anymore. It grows gradually with respect to time. So if I plug this back in, I will have divergence of E cross H conjugate would be equal to if I plug this back in, I will have something that looks like what I had before. Okay, J omega mu of omega H square plus J omega epsilon star E of t. Okay, I want to emphasize the fact that these are not constants anymore. Okay, this is gotten by just using this equation. I just use this equation. This times this becomes magnitude square. This times this becomes magnitude square. And if I rewrite it, I have these equations over here. But omega is a complex number. Okay, omega is a complex number, and I better make sure that I didn't make a mistake here. That should be a complex conjugate on this thing. And if you write this out more carefully, it will consist of a real part minus an imaginary part, mu of omega H of t square, okay? And then the second term will be J omega prime plus J omega double prime because of the complex conjugation. And then epsilon star of omega E of t squared, okay? With the emphasis that these are not constants anymore because of this behavior, because the time dependence does not cancel, okay? And then I'm going to assume that mu, which is now, mu is a function of a complex frequency, which is a complex frequency with a real part minus a small imaginary part, okay? And that I can tailor it, series expand this and say that this is approximately equal to mu of omega minus J omega double prime, okay? And by the Taylor series expansion theorem, this would be just equal to that. I'm just doing a Taylor series expansion, assuming that this is small. This is the leading term, this is the first order term. I can also do the same thing to this term over here. So I'm going to do, I have done that to that term over here. The next thing I should do is to do it to that term over there. And then I can show that epsilon of omega conjugation, or maybe I just do it without conjugation first. And then this by the same token, let me see, what am I doing here? That epsilon of omega then would be just equal to epsilon of omega prime minus J omega double prime, the epsilon of omega prime over the omega prime, okay? So any questions so far regarding the derivation? It's kind of hairy, kind of intricate, but it's quite straightforward. You can follow the math logic. Okay, so I'm going to do Taylor series expansions on this. And I'm assuming that omega double prime is very small. Okay, any questions so far? So the next thing is quite hairy. I'm going to assume that this term is small. This term is small, and then I'm going to plug into the above expression. I'm going to assume that this term is small. This term is small. Okay, so if I have a small term, the product of two small terms would be even smaller. So I'm going to keep only leading order term, is what mathematicians call leading order terms. Okay, if you keep only leading order terms, and then rewrite this equation. You rewrite this equation keeping only leading order terms. You can show that the leading order terms are given by divergence of E cross H conjugate. Okay, the right-hand side, if you keep only the leading order term, you will have a term that comes from J omega prime, mu of omega prime. Okay, I keep only the leading order term, which is this term times that term, and then times H T of square. Okay, keep the leading order term from this. I will get 4 terms. Okay, I get 2 terms from here, 2 terms from here. Because of these 2 terms, I get 4 terms. I only keep the largest term. And similarly, I do the same thing to this term. I keep the leading order term from that term. Okay, I will have epsilon star omega prime E star. Okay, I keep the largest term there. And then I keep the next order terms. Okay, the next order term will be terms that are involving omega double prime only. And then mu of omega prime. For instance, if I look at this term over here, okay, the first term was already written down. The second term will be the product of this term and that term. Okay, these 2 terms. The product of these 2 terms will be that term. And then I can write down H square. And then I also do the same thing to the other term, that because there are 4 terms here that involve omega double prime. There's one coming from here, but mu also has an omega double prime. So there is another term that involves omega double prime. Okay, partial mu, partial omega prime, H squared. Okay, so I take this term and keep the leading order term plus the next order term, I get this, okay? And then I do the same thing to this term over here. Keep one term coming from here, and then epsilon has 2 terms. It will be a term of this multiplied by that, and then this term will become something like omega prime or double prime, epsilon star of omega prime, E squared. And then I will have omega prime, omega double prime, partial epsilon of star, okay, partial omega times E squared. Okay, so quite a bit of doing, but what am I trying to get at? What I'm trying to get at is that the right-hand side looks very complicated now. Okay, right-hand side looks very complicated now. But what I'm able to show is that divergence of this is equal to these 2 terms on the right-hand side plus this second order terms. But this second order terms can be combined. Like these 2 terms can be combined into 1 term, because I know that partial omega mu partial omega can be written as mu plus omega partial mu partial omega. Okay, so I can use this identity to combine these 2 terms. Okay, because I have omega prime here and so on. If I use that, then I can rewrite the right-hand side more simply as divergence of E cross H star being equal to minus J omega prime mu of omega prime H squared minus epsilon star omega prime E squared. Okay, and then because I was able to combine the 2 terms into 1 term, I only have 2 terms left. The second part that looks very complicated can be written as this. And then H squared. Okay, plus partial omega prime E squared, okay? But then there's some beauty in being able to rewrite this thing in this way, okay? There's some beauty in being able to write this thing in this way, because now if I were to take the imaginary part of this equation, the first term will be purely imaginary. Okay, the first term will be purely imaginary, and it will be picked up by the imaginary part of this equation. But however, if I were to take the whole equation and take the real part, okay, take the real part of the whole equation, the first term will drop out. So you will have divergence of the real part of the left-hand side. And we know what this is. This has the meaning of time average power flow in the limit when omega double prime goes to 0. And then if I were to take the real part of the right-hand side, I will pick up this term over here, okay, minus omega double prime over 2. And let me put a half over here, because I know half the real part has the physical meaning of time average power flow. So if I were to do that, then if I do everything carefully, okay, the right-hand side can be written as this. You can follow the math in the lecture notes more carefully, but this is what you have finally. And I have convinced yourself, or can convince you, that this is not a constant of time, but something that is weakly growing with respect to time. Okay, it's weakly growing with respect to time. So you can think of the right-hand side as being proportional to partial t of these weak functions of time. Okay, because this thing, as I said before, the product of this field, E squared, will also have to grow with time. H squared will also have to grow with time. And so you can think of this as being the same as, let me see, did I mess things up? Okay, this is the same, what did I do? I go into the display mode. How do I get out of the display mode? I need a keyboard, but I don't see a keyboard at the bottom of my, oh, here's the keyboard. I press the escape sign. It should get me out of the display mode. It doesn't get me out of the display mode. So no luck, I'm in the display mode. I have to open my keyboard up and press this sign. Now it gets out, okay? Very strange. The electronic keyboard wouldn't get me out of the display mode, but this other thing would do. So I can think of my right-hand side now as being the same as okay, right-hand side has been the same as being equal to partial t of some stored energy of some kind because of this omega double prime over here. Okay, this is actually, sorry, this should be 2 omega. Okay, so this is something to be like that, and then you can actually write this equation as something like divergence of, you can write the right-hand side as minus partial t of Wt. And you can get very strange, you can get this very strange formula for energy storage. Okay, the formula for energy storage now is given by this rather complicated looking expression. Rather complicated expression, something that you never learned before. Okay, So what is the difference from something that you have learned before? Well, let's assume that you go back to the case when the medium is no more dispersive. If the medium is no more dispersive, then you know that this has to be true. Let me see. If the medium is no more dispersive, well, problem is that it's upside down on my keyboard. I don't know why is it upside down in my computer. It refused. Oh, it flips up again. Okay, so if mu is independent of frequency, epsilon is independent of frequency, then this quantity would just be equal to just mu itself. And then this other quantity would just be epsilon itself. And it's going back to a formula that you're familiar with. This is just epsilon h e squared, and this is just mu h squared. Okay, so those are some of the formulas that that you should be familiar with. Okay, are there any questions so far? Any questions? So what we have learned in this lecture is a way of writing down the energy storage for a dispersive medium. The lesson learned here is that the formula that you have learned previously does not hold true anymore. Okay, does not hold true anymore, which is that this thing that you learn either in an undergraduate course or freshman level physics course for energy storage in an electromagnetic medium. And if the epsilon and mu are functions of frequencies, then you actually have to augment energy storage formula with one that looks more complicated like this, okay? Where the energy storage, let me see where the complicated formula should be, with one that looks something like this, okay? And the derivation is complicated, but written out very carefully in the lecture note. And I'm sure that you can follow it if you follow the lecture note. There's one lesson learned. Another lesson that we have learned in this lecture is the fact that if you have a medium that is anisotropic, okay, and if you go through the complex pointing theorem, okay, which is this one over here, if you go through the complex pointing theorem and understand what the real part and the imaginary part of a complex pointing vector is, you can show that if the medium is lossless, which means that it doesn't dissipate energy, the time average power flow through that medium must integrate to 0 on this surface, which means that this thing in here must be pure imaginary, okay? Which means that this has to be pure real. And in order for that to be pure real, then the permittivity tensors have to be Hermitian. Okay? Yeah, anything, any questions? Any questions? Okay, that was the second lesson that we learned. And then the third lesson that we learned is that electromagnetic waves carry a momentum. The momentum is actually very similar to power flow. And then you can show that the momentum density is given by this formula. And you can derive it.
Oh, okay, you're good. Like this.
Yeah, hello. I hear some noise in the background. Are you okay? You guys okay? So we get this very nice formula for momentum density. The derivation in most textbooks are very complicated. You can look at Jackson, you can look at Kong, but I'm just giving you a very simple particle picture. Okay, any questions so far?
Hi, Professor, I have a question.
Yeah, sure, please.
So what is the physical meaning for the imaginary part for the angular frequencies? Why we induce that?
Oh, the imaginary part of the angular frequency, for most analysis that we had in the past, we assume a time harmonic signal. Okay, let's go back to this slide. We assume that the signal is time harmonic, so omega is a pure real number. If we allow the fact that omega is not real, that means that it's not time harmonic anymore. And if we make the imaginary part very, very small, we can call it quasi time harmonic, almost time harmonic, but with a small growing part. Okay, this quantity here will grow with respect to time. Okay, so it's quasi time harmonic, which means that this thing is not constant anymore. Because it's not a constant anymore, it has to obey a different kind of energy conservation law. And from this new conservation law, we can actually deduce what the energy density should be for dispersive medium. So it is a mathematical tool, a mathematical trick to make things such that what we have is not purely time harmonic anymore, but quasi-time harmonic. Okay, quasi-time harmonic. And because it's not time harmonic anymore, it has to have a different kind of behavior. And using that behavior, we can look at energy flow in a different fashion. The physics is more difficult to understand. And you can stare at the physics, you might understand it, but the mathematics is quite easy to follow. Okay, it might take a while for you to get the physics to sink in. You really have to think a little bit. What does the math mean in terms of the physics? Okay, so any other questions? That's a good question because we are doing some kind of analysis that we never did before, which is using a signal that is not time harmonic anymore. But it gives you physical meaning and new insight that you can use to get energy storage formula that you never learned before. What this means is that if you were to generalize this to a capacitor or inductor, if the inductor is a function of frequency, if the capacitor is made of medium that's a function of frequency, you will have to change the formulas for a capacitor and an inductor. The energy storage formula will be different. Even in circuit theory, it'll be affected. Okay, I'll let you go. Okay, I have an office hour this afternoon at 3 p.m. if you want to come to office hour today. Okay, I'll talk about transmission line in the next lecture because I think we don't have enough time to go into transmission line theory today. Okay, I'll stop here and let you go. Or do you have more questions you'd like to ask?
Oh, thank you, Professor.
Okay, I'll see you later then.
Professor, would you be recording the office hours?
I can record it if you request it. I usually don't.
Oh, okay, because I actually have another obligation at 3 p.m. So it would be personally helpful if you would be able to record it and then send it afterward.